All right, folks, we'll do about 15 or 20 more seconds. Say 245, 245. A few more seconds, just guess if you're not sure. Okay, that's pretty good. B is the right answer. A couple steps you want to take here. First of all, we know that our force is equal to 500 newtons. That's given here. I want to know what the mass is. Since I know F equals ma, I know that the mass is equal to the force divided by the acceleration. So now I need to find the acceleration. I know that v naught equals 0. I know that v final is 3.9. And that this change in speed occurs over 12 seconds. And so acceleration is v minus v naught over t. And this works out to be, 3.9 over 12. .325 is what I got? Yeah? Okay, so that's 0.325. And then I put that meters per second squared here. And I get my mass is 1,500 kilograms. All right, let's see if there's another one we can do here. Don't forget that our exam is coming up. So we have Monday when we return after the break, and then Wednesday is the exam. I know it seems like we just finished an exam, but that's how it happens when you have 4 exams. They come right after another, one after the other. Okay, hey, let's do number 16. We've done one similar to 16. Well, let's try this one. Woman who weighs 700 newtons steps onto a scale that is in an elevator. The elevator begins to accelerate. The woman now weighs 500 newtons, according to the scale. The acceleration of the elevator is which of these? This is a lot like that elevator problem that we worked with the block hanging by a string, wherein the tension in the string would be a lot like what the scale is reading here. Oh, let me start the clicker base. Remember, you can get rid of a couple of these answers. She weighs less, or she appears to weigh less, than when the elevator is not moving. So ask yourself the question, is the elevator moving up or is it moving down? When will she appear to feel less weight? Is it moving up or moving down? And then when you can determine that, you can get rid of either A or B or C or D. We're going to stop in about 10 or 15 seconds. Let's stop at 220. 220. 10 more seconds. Doing pretty well on this. 220. Okay, good. B is right. This one's a little bit different from what we did with the elevator, but it's a lot the same. I'm going to draw a picture first. We have a scale here. We have our lady standing on top of it. I know that she has a weight, FW, that's equal to 700 newtons. However, I know that she feels like she weighs less than that. So that would be like this force, and this force is equal to 500 newtons. And then I want to know what is the acceleration. All right? So I start with my Newton's second law. Sum of the forces equals mass times acceleration. And I want to solve for this acceleration. In the course of that, I also need to know what the mass is, so we'll have to figure that out. So I'll say 500, that's the upward force right here, minus 700. It's negative because it's down, vector, negative vector. And then we need to know our mass. So our force weight equals m times g. So our mass is equal to Fw divided by g. That's going to be 70 kilograms. So she has a mass of 70 kilograms. I said 700 newtons, which is our weight, divided by 10, which is the acceleration due to gravity, and I get 70 kilograms. This is equal to 70 kilograms times the acceleration. And then I solve for the acceleration. So it's going to be negative 200 newtons divided by 70 kilograms. That's equal to my acceleration. It's negative, so it has to be down. And it's going to be B is the right answer. So 200 over 70 is about 3. So again, I start with my Newton's second law. I start just by thinking about the situation. And I know that I have a weight that's downward. And her apparent weight is going to be like the force that the floor is pushing up on her with. So like if she felt weightless, then this force would equal to 0. It's like she would float up off of the floor. She wouldn't have any force pushing up on her. Or if you want to think of it as the tension in the rope, imagine her hanging from a rope. Then this would represent her weight, like the tension in the rope. It's the exact same problem. It's just there's no rope. We have the floor exerting the force instead of the rope. And then we can say, well, since she feels lighter than she actually is, the elevator must be going downward, just from experience. Ever been in an elevator that goes down? It sort of lurches a little bit? Maybe. Not this elevator, a fast elevator. But regardless, we can say the sum of the forces equals mass times acceleration. That's Newton's law, Newton's second law. This is my positive force. This is my negative force. This is my mass, which I have to find because it's not given. The weight is 700 divided by the acceleration due to gravity, which is 10. And then that gives us, we can solve for acceleration for negative 3. All right, let's see what else. We'll come back to this and these. We'll stop right there for now. Y'all had a good weekend? Yeah? Had a pretty good weekend, too. We did these problems. Let's go. We still haven't done the third law, so we're going to cover the third law today, and we'll do some more practice problems, too. Okay, so we've been using the unit of the force. It's the Newton. By the way, with abbreviations of units, anytime the unit is a person's name, like Newton is named after Isaac Newton, when you write it out like this, you don't have to write this down, but when you write it out like this, you lowercase it, unless you're actually writing the person's name and then you uppercase it. But when you're writing the unit, you lowercase it, but when you abbreviate the unit, you uppercase it. Y'all know that? That's why some units are capitalized, like the Newton and the watt, and I don't know what else. But some units are not capitalized, like the gram and the second, because those aren't named after people. But in this case, the unit of force is the Newton, which is abbreviated with a capital N. In the United States, the unit for force, do y'all know what the unit for force is? It's the pound, right? Oh, we often use a pound for mass, but that's not really the unit for mass. Do you know what the British unit for mass is, by the way? So I think somebody said it. What? Stone? Maybe that's right. I always thought it was the slug. Oh, well, I might be wrong. Maybe it is a stone. I thought it was the slug.
Like I weigh stone 6 pounds, something like that. It's like a measurement of weight.
It's not that important, but I'm curious now. British unit for mass. Imperial ton. That's all weight. It is the slug. I was right, but you might be right too. I'm not sure. I've never heard that. I don't see stone there. Okay. I'm going to write slug. You don't need to know that. I just think it's kind of good trivia to know. Typical person weighs about 700 newtons. An apple, you know, like the proverbial apple that fell on a Newton's head, which I don't think that ever really happened, but an apple is about 1 Newton. All right? You also need to know, as we move into these more complicated units, sometimes you'll see questions on the test that ask about the basic SI units of that unit. So for example, with the Newton, remember we get this from F equals ma. The basic SI units of a Newton is 1 kilogram meter per second squared. And I just get that from saying the mass, which is in kilograms, times the acceleration, which is in meters per second squared. So increasingly, as we move into further and further chapters, we'll get these units that are really made up of a lot of different units. And so sometimes on the exams, I might ask you, what are the basic SI units? And this is all you do. You just start with your expression for force in this case, which is mass times acceleration, and then you break these up into their basic SI units like this. Don't try to memorize them. Just go with the equation, and then you can determine the units if you see that type of question on the exam. Let's try this quick test question. By the way, I don't know why I put so many true-false questions, because I don't really use true-false questions that much, but because they're kind of difficult to read. But is this statement true or false? It is possible to have motion without a force. Is that a true statement or a false statement? Think back, I don't know, Newton's first law. Ask your neighbor, y'all are split between A and B pretty much evenly. Ask your neighbor what they think. Say, it is possible to have motion without a force. That would be true. Or, it is not possible to have motion without a force. All right, we're moving more in the right direction. I'm going to stop at about 1:15, so just 10 more seconds. 1:15. It is possible to have motion without a force. In fact, don't even think of forces as causing motion, although they do. Think of forces as changing motion, that an object's motion will change if a force acts upon it. If no force acts upon it, the object's motion will remain the same. And that is Newton's first law, that an object remains in its state of motion unless it's acted upon by an external force or a net force. We're going to skip this one because it just doesn't really make any sense. Okay? All right, let's look at the gravitational force, and then in the process of this, we'll look at Newton's third law as well. Newton's law of universal gravitation just describes the force that you have between two objects of mass, and he used this to describe the force, by the way, between the Earth and the Moon, but it applies to all objects of mass. He found that the force is proportional to the mass. that is the force between these two objects. I have two masses. They both experience a force that is proportional to the mass and proportional to the 1 over r squared. He didn't measure this. Actually, the gravitational force can be quite difficult to measure between two objects of mass, but he calculated it using something he called the shell theorem, which he invented. Isaac Newton, man, smart guy. He was a very smart guy. He's probably one of the smartest people that have ever lived in the history of time. Isn't that cool? Anyway, so he determined this law of universal gravitation, and he found that the force between two objects of mass is equal to G times M1 times M2 over R squared. G here is the gravitational constant. It is, G is equal to 6.67 times 10 to the minus 11. You don't need to know the number. If you need to calculate anything with this, I will give you that number. It is in units of Newton meter squared over kilogram squared. Is that right? Yeah, so that gives me units of newtons for my force. So a couple of things I want you to recognize. Do you remember in the incorrect laws of motion that Derek said that if you have the Earth and then up here you have the moon, that the Earth exerts a big force on the moon, but the moon exerts a small force on the Earth? Do you recall that? Was this correct or incorrect? That's incorrect. That even though the moon is so much smaller than the Earth, it still exerts the same force on the Earth as the Earth exerts on the moon. In fact, you know what? The Earth right now is exerting about 700 newtons of force on you, roughly. You are also exerting 700 newtons back on the Earth. Wow. Take that, Earth. 700 newtons right back at you. Okay? This is a nice application of Newton's third law, that for every force we'll have an equal and opposite force. We'll get back to that in just a second. And so, you know, Newton's universal law of gravitation is not terribly important for us. You're probably not going to see, well, let me see. Yeah, you might see some conceptual questions regarding it, but I'm not going to ask you what is the force between two masses, okay? But I do want you to understand that the force between two masses is the same. That is that F12 is equal to F21, or the magnitudes are the same. They're actually equal to the negative of one another, because one points in one direction and another points in another direction. Okay? Y'all clear on what I mean by that? I'm not going to have you calculate the force between two masses, but I do want you to understand a couple of things. One, that these forces are equal and opposite, even if the masses are vastly different. And then also that this force is proportional to the mass, and the force is proportional to 1 over r squared. So for example, if I have two masses, and then I put them half as close again, what happens to the force between the two masses? First of all, does it get bigger or smaller? If I take two masses and I decrease their distance by a factor of 2, does the force between them get bigger or smaller? It gets bigger. Does it increase? Or by what factor does it increase? No, it doesn't increase by a factor of 2. Let's say that I decrease the distance by a factor of 2, so I halve the distance. Then what happens to the force that is acting upon those particles? It doesn't double, no. It doesn't have. It quadruples. Right. I'm sorry, who said that? Yeah. It quadruples. Because if we look at this expression right here, if I have r squared, if I have r and then I square it, then that's going to give me a factor of 4 over here. So you will see some questions like that. If I change the mass or I change the distance between the particles, what will happen to the force? Right? And then also this idea that these are equal and opposite forces. It's a nice application of Newton's third law. Okay? So in Newtonian physics, forces are instantaneous. However, we've always had this, that we have our forces, our contact forces are always instantaneous, that whenever you make contact, those forces occur. However, with the gravitational force, this is a field force, and so it's not necessarily instantaneous. Einstein theorized that if you took away the sun, that the Earth would continue to orbit around the sun for, I don't know, about, 8 minutes, I think, which is the amount of time that light takes to travel from the sun to the Earth. Did I write it there? Yeah, I didn't write it there. But he predicted the existence of these waves that transfer the force of gravity, and those are called gravitational waves. Have y'all heard of gravitational waves? They were discovered here in Louisiana and in Washington. So, anybody ever been to LIGO? I went too. Wasn't it cool? It was really awesome. They're only open like one Saturday a month, but it's really neat. They show you around into the control room, and they have all these really cool demos for waves and stuff like that. Right? Did you get to see the? Oh, me too. I thought it was just me, but I guess it's everybody. If you go, you'll get to go in too. All right. But anyway, LIGO, they detected these gravitational waves. See, they have more about that. Yeah, we're going to watch a video, but let me tell you in short what LIGO does. And you'll have some basic sort of ideas about what LIGO is and what it does. I'll show you as we go through this, and I'll show you a little video about LIGO. LIGO is the Large Interferometric Gravitational Observatory. What it is it's two long arms. So you have like the control center here, and then you go out. I think it's something like 5 kilometers. I could be wrong. It's really far away. So you have one arm in that direction, and then you have another arm in that direction. They have lasers down here, and then down here they have mirrors. And the really hard part about this is all 3.1 miles or whatever of this arm is all vacuum sealed. So these lasers are traveling through a vacuum. It's very difficult to get a good vacuum that's 3 miles long. And when they travel down, they bounce off the mirror and then they come back. And then similarly, you get the same thing over here. They travel down, they bounce off the mirror, and then they come back. And when they come back, we're going to talk about interferometers next semester when we get into light. But when they come back, they combine those two lasers, and they're able to measure very small changes in distance. That's approximately equal to the wavelength of the light. So they can measure very small changes in distance with these lasers. Now, over here in outer space, you have two black holes, and they're doing their little dance, and they collide into one another. Or some other cosmic event where you have this huge star that blows up in a supernova, or a neutron star that's spinning really fast, that's very massive, some very massive event. In the case, I think the one that they detected was a black hole merger. You have two black holes that are going around one another, and they collide into one another. Out in outer space, they have this thing, and it emits gravitational waves. Gravitational waves basically don't interact with anything. So they'll travel through stars, they'll travel through galaxies without really changing the gravitational wave at all. And then they come to LIGO, and they travel through this space where these lasers are traveling, and they change the distance. They shrink space as they go through. So they'll shrink this distance by a small amount, and they'll lengthen this distance by a small amount. So when the gravitons actually travel through LIGO, this distance will actually get shorter. I'm going to exaggerate it. It's like the actual space just shrinks a little bit. And this distance over here will actually get longer, just by a tiny, tiny amount, but an amount that's measurable. And that's what they did back, gosh, I think it was last spring or last fall. They detected the first gravitational waves. I have a video I'll share with you. Where is it? I'm gonna have to pull it up on YouTube. Give me just a moment. There's not a whole lot of immediate payoff. I mean, in some sense, we don't really still understand what gravitational waves are, but in some sense, we'll be able to observe things in the universe that we had never been able to observe before by looking at these gravitational waves. But then the hope is that one day we'll actually understand how this force is transferred between objects of different mass. Because right now, we don't really know. We know that there is a force between me and the Earth, but we don't really know how that force is transferred or what physically is happening there. We just observe it. And that's what Newton did, is he observed it and he described that force, but he didn't really know what it was. There are some like Superman aficionados, anybody like Superman, that say that Superman can fly. It's okay, you can raise your hand. That Superman can fly because he's able to manipulate the gravitational field, that he's able to manipulate these actual gravitational waves. So maybe one day we'll be able to fly like Superman. That would be pretty cool, right? All right. All right, so we've already talked about the weight, which is the force due to gravity. So I'll just sort of do it briefly here. But this force weight is equal to m times g. And so, for example, if I have an object that has a mass of 10 kilograms, then the force weight is equal to 10 kilograms times 10 meters per second squared. This is the same acceleration due to gravity that we had in Chapter 3 when we were doing projectile motion. This is equal then to 100 newtons. We've already used that a number of times. So if ever I give you the mass, just remember you need to multiply it by 10 in order to figure out what the weight is. Also, for Newton's law of gravitation, it's fairly simple to derive the acceleration due to gravity. I'm not going to require you to do this, but since it's a simple derivation, I'm going to show it to you here. I know from Newton's universal law of gravitation that F is equal to G times m1 times m2 over r squared, right? The force between two objects. And so if I make this m1 and this m2, then I can call this, I'll just call m1 the mass of me and m2 the mass of the Earth. So I'll rewrite this as g little m, big M, that's the mass of the Earth, divided by the radius squared. Now I also know that F is equal to m times g, this force weight, and this is also the force weight. So I can set these two equal to one another, and I get an expression for g, which is dependent only on the mass of the Earth and the radius of the Earth. So this is another expression that we can have for the acceleration due to gravity, which is just based on the mass of the Earth and the radius of the Earth, and then that gives us the acceleration due to gravity. This is pretty powerful. Can you imagine why this would be powerful? It basically says that if you can measure the acceleration due to gravity, which you all did, you did it in lab. It's pretty simple to do, actually. You can do it with a pendulum like you did in lab, or you can do it by watching things fall and measuring the time that they fall in. But if you can do that accurately, then you can measure the mass and the radius of the Earth. So there's actually a mission called the GRACE mission. It's put up by NASA. It's been going for a number of years. The GRACE mission, what it does, is the Northern Hemisphere, is it's a satellite. It's a satellite that travels around the Earth, and inside this satellite you have a pendulum that goes back and forth, and that pendulum measures the acceleration due to acceleration due to gravity. So there's a pendulum, just like you did in the lab. You measure its period, and then you determine the acceleration due to gravity. So why would you want to determine the acceleration due to gravity as this satellite goes around the Earth? The acceleration due to gravity is dependent upon the mass and the radius of the Earth. So what would be some things that would change the acceleration due to gravity as you go around the Earth? The shape of the Earth, right? So like if you go over Mount Everest, you have a lot more mass underneath you, and so you're going to have a bigger acceleration due to gravity. What else? I'm sorry, what? Orbit? The orbit, like how high you are in orbit? Yeah, if you're further away, then you're going to have a lower acceleration due to gravity. If you're closer, then you'll have a higher acceleration due to gravity. One other thing, it's sort of related to the mass, is that if you have things that are underneath the surface of the Earth, then you can map out where those things are. So Grace is able to, I don't want to say map, but is able to detect things like water tables, oil deposits, and other things that you can't see from the surface of the Earth. Large subterranean geological formations that you can't see otherwise. Just by measuring the acceleration due to gravity very accurately, and then how that changes over the surface of the Earth. Okie dokie? All right, let's, okay, so the acceleration due to gravity on Earth is 10 meters per second squared. We've already seen that. And the sun, is it bigger or smaller if you're on the sun? It's quite a bit bigger because the mass is bigger. On the moon, it's smaller. How about on Mars? Mars is a much smaller mass planet, so it's smaller. Remember, this acceleration due to gravity is gm over r squared. How can a body then with less mass than the Earth have a greater acceleration due to gravity? If you had a body, say like Mars, how could you give it a bigger acceleration due to gravity? Or say you had, I don't know, a neutron star. Neutron star? No, we can't have a neutron star outside the planet. But something like that, that has a very large acceleration due to gravity, but a small mass. How could you get that? You change the density, or you change the radius, if you make the radius a lot smaller. So remember, G is equal to, or excuse me, little g is equal to big G m over r squared. And so if m is constant, and r decreases, the acceleration due to gravity will increase. If I keep this constant, if I make this smaller, that means this will get bigger. Let's skip this thing about on the moon. It's not terribly important. Okay, so now let's get to Newton's third law, and we'll do some more clicker questions here in just a minute. Okay, so if objects 1 and 2 interact, the force F12 exerted by object 1 on object 2 is equal in magnitude but opposite in direction. So for example, if I have an object here, it has a certain force acting downward, say the weight. Let's say that this weight is equal to 20 newtons. Then there's going to be an equal but opposite force that is pushing back on the object that will also be equal to 20 newtons. If I push on the board with a certain force, the board pushes back on me. All right? All right, if Nelson Zamora slugs me in the cheeks, in the face, then my face will push back onto his fist, or vice versa for me, or whatever. All right? Anytime you have a contact force, I will have a force that's equal in magnitude but opposite in direction. And that's true also for field forces. Here's the Earth, here's the moon. I have a force in that direction and a force that's equal but opposite from exerting the moon on the Earth. So anytime I have one force, I'm going to have an equal and opposite force. And the result of this law You guys ready? It's gonna blow your mind. You ready? This is actually kind of a big deal, that the result of this law is that no isolated force exists. That you can never have a single force. You can never have a force that doesn't exist without another force that's equal but opposite. Weird but true. What about the force due to gravity exerted by you on the Earth? Is that an isolated force? No, because you're doing what? Right. 700 newtons right back at you, right? So if here's the Earth, here's you. The Earth is pulling down on you with 700 newtons of force, but likewise, you are pulling right back on the Earth. As I said, also contact forces observe Newton's third law, and the result of this is something we call the normal force. Normal not in like usual, but normal in its mathematical sense. I know what normal means in a mathematical sense. It means this. It means that you're perpendicular. You know what I'm talking about? That normal means perpendicular. So if I have an object, like consider that block on the table. I have an object that has a weight of 20 newtons. This force that pushes back on the object is called our normal force. So anytime my normal force, or anytime I have a force that's pushing down onto a surface, that surface will push back up in the opposite direction, and that's called our normal force. The normal force is always perpendicular to the surface. Sorry, hold on. Yeah, so imagine we can go, if we imagine this table again, we have our object, say it's 20 newtons. If we want to know our normal force, we can go through this process. The sum of the forces equals mass times acceleration. Since our acceleration is equal to 0, in this case, it's going to be Fn minus Fw is equal to 0. So Fn will equal to Fw, which is going to equal 20 newtons. So anytime you have a horizontal surface, Fn will be at least equal to the weight. In some cases, we'll see that it's not, that it's actually bigger than. So I'm going to write it like that. Anytime you have a horizontal surface, the normal force is either equal to or greater than the weight of the object. We'll see, we'll deal with this. There would have to be other forces at play. If you just have a single force, the weight in this case is going to be equal to it. The normal force is also always perpendicular to the surface. All right, we're going to get into inclined planes. Probably not today. We'll probably wait till Wednesday to get into them. But in an inclined plane, if I have something like this, an inclined plane, I have a block on an inclined plane, the normal force will be perpendicular to the surface. So the normal force isn't always up and down. It can be to the side. In fact, if I push on this in this direction, what is the direction of the normal force? To your left, right, up, down? It's to this direction. I'm pushing to your left, and so the normal force is in the opposite direction. Let's see, let's do some more clicker questions. We just have about 5 minutes left. I think we did some of these last time, all right? Where did we leave off? We hadn't started them at all? Oh man, I'm sorry. All right, a book is lying at rest on a table. The book will remain there at rest because which of these? Why does the book remain at rest? All right, just a few more seconds. I'll stop at 58. 58. Okay, let's see. D is right. The book will remain there at rest because there's no net force. You can think of this in terms of the first law or the second law. Right, the first law is the law of inertia. It says that an object will remain in its current state of motion unless a force acts upon it. And so this object, which is at rest, will stay at rest unless a force acts upon it. Or you can think of it in terms of Newton's second law, the law of acceleration, that F equals ma, that this thing's not going to accelerate unless a force acts upon it. Are there forces acting on the book? Yeah, I can think of two right off. Can y'all think of two? Gravitational force and normal force, just like Gordimer-Gibbons. Do y'all know Gordimer-Gibbons? Y'all watch that show? Oh, I'm sorry, it's a good show. The normal force? The net force is the sum of all the forces. So on my book here, I'm sorry, we just watched the season finale of Gordimer-Gibbons yesterday. So it's on my mind. The force normal is up. The force weight is down. The sum of these forces would equal to 0. All right? So there's no net force. A hockey puck slides on ice at constant velocity. What is the net force acting on the puck? I think first law, second law? Second law, probably. Feel free to ask your neighbors. Y'all are sort of spread around here as to what the answer is. I'll stop at 50 seconds. 50. It's 5 more seconds. Okay, E is the right answer. I know that the net force is 0 because it's moving at a constant velocity. And if it's moving at a constant velocity, that means the acceleration is equal to 0. So since the acceleration equals 0, the net force, which is mass times acceleration, is also equal to 0. You put your book on the bus seat next to you. When the bus suddenly stops, the book slides forward off the seat. Why? Almost everybody in my 201 class got this wrong. Let's see if things are a little better. Why does the book slide forward off the seat? Hey, y'all doing great. More have it right than wrong, but we still have a lot of students with it wrong. So feel free to ask your neighbor. I'm going to stop at 55. 55. Just a few more seconds. Okay, B is right. No net force acted upon it. It was moving along at a constant velocity, and then it kept moving along at a constant velocity, even though the bus stopped. If it was going to stay on the seat, what would be the force that would likely act upon it? Somebody holding it, somebody put their hand out, or maybe friction between the seat and the book. Yeah, that would be a net force acting upon it. All right? Are we out of time? Yeah. We'll call this a day. Enjoy. Oh, now it's time. You have a great day.